can proceed with our lecture. Today, since last time I did it too long, so today we'll end up a little bit earlier. So the topics which are necessary for today will be covered, but we'll save some half an hour, which was longer last time. Okay, we have discussed the basics of one-dimensional issues on thermal stresses. We'll discuss the bars first. Firstly, separate bars. So a single bar, which was the basic case that was fixed at both ends, so there was no possibility for any deformation. Let's recall the information that the increase or decrease in temperature, so changes of temperature generate the deformations in a body. And if the body is not constrained and it's equally heated or cooled, so the distribution in the material, the temperature distribution in the material is it's the same, so that there is a constant temperature at a given time. So we have no distribution within the body, and there is no external constraints, so the body can freely deform. There will be no stress. The stresses are a result of interaction between object that is heated or cooled and the forces generated by the surrounding body, so cooperating body, the body that are attached to our object. And due to the changes, for example, in temperature, so changes in deformations in both objects, stresses occur. We also said that we can slightly or to some extent decrease the stress that is generated. So the worst case is when object, let's say we discussed a stride bar, which is fixed between two rigid walls. Rigid walls means that these walls do not deform at all, they do not move. So the object of our interest has no possibility to deform. So since it wants to deform, it exerts force on the support. The support on the basis of the third Newton's law provides an opposite reaction, and to be honest, we have a compression of the body due to the reactions. And we can slightly release this reaction by two possibilities, two possible actions. One was the thermal gap between the supports, let's say. So the object is not exactly fit into the area, but there is a slight gap between, let's say, the wall, the constraint, and the object. So it can, to some extent, freely extend, freely deform, and only a part of the temperature increase provides such an elongation that it comes into contact with, let's say, the support. This is one possibility. So the bigger the gap, the lower the stress. Of course, we can reach such a gap level that the bodies will not come into contact, so the stress will be zero. But this is quite a rare situation where we can install or support object in such a way that there is no contact with other objects, with other supports. And the other possibility is to provide a elastic support, which means that let's say instead of rigid wall, there is a let's say spring element. Let's say it could be a spring, generally generally understood, so that the element that deforms under the force. You know, usually we have discussed the issue that the spring force is linear function of the formation. So you can reduce, so not completely eliminate the force or stress produced by the temperature difference, by temperature increase or decrease, but you can reduce it significantly, of course, depending on how stiff the spring is. But generally we can do such actions. So the worst case is rigid connection and some solutions, some release of the stresses is possible due to thermal gap or spring connection spring element in the system. And next we started, so we finished exactly our lecture with bars working in parallel. So two objects connected together, and we discussed the first thing, which was the issue. We have two members, two bars in parallel. They are fixed at left end, let's say, and on the right hand side they are joined together, but they are joined by a rigid plate, so they cannot deform independently. Look at this. If we increase the temperature, let's say we have the same materials, the same lengths, so if we increase the temperature or change the temperature in a different manner, one of the objects will try to extend or deform, generally say deform because it depends on the direction of the temperature change. So one of them will deform more than the other. So let's assume that they are heated up. If, let's say, the upper one would be heated more than the lower, it would try to pull the lower one. So we'll try to put in tension the lower one. On the other hand, the lower one, due to lower deformation, would let's say constrain somehow elongations of the first one. So there would be a mutual interaction between these two members. And we discussed this issue and we tried to find out what the interaction will be. We assume that we have a temperature increase, different temperature change of both members, so delta T1 and delta T2. They could have different lengths, then they can be made of different materials. So this, let's say the formulas are quite general here. And we try to find out what are the loadings. So here is the total elongation or total change in length of the entire system. And it depends on what are the temperature changes and what are the materials. Look, there are two material properties, E, so Young's modulus and expansion coefficients, but also we have here geometry data. So how, let's say, massive the object is, A1, A2. We have also length, because on the length depends the elongation. So this is the total elongation of the entire system. What we will observe at the end on the right hand side. On this basis, we calculated stresses, and they also depend on the parameters discussed before. So the materials, geometry, and the temperature change. Here we also have a factor connected with force applied. So if there is a force applied to the system, there's an additional term. If force is 0, it is of course zero force applied here, provides that this factor here in numerator is cancelled. So we have only that one. All right. And we have generalized this topic to n bars in parallel, so a bigger number of bars than more than 2. So it can be written in such a form. We have force, external force applied to the system. It may be 0. And here we sum up such factors: Young's modulus, cross-sectional area, expansion coefficient, and change in temperature for a given member. So we treat every member separately and add such factors together, and we divide it by, again, sum of such factors. So this is the rigidity, E times A, divided by L. So for each particular member, so depending on how much of the members are present there. And on the same manner, we can calculate stresses in each bar. So for any bar in a system, if we have more than 2, for 2 we have a ready formula. If there's more than 2, we can calculate stresses in any bar. Of course, separately for each bar can be determined stress which occurs there. And we discuss, of course, some example. This was discussed, and this was not discussed as far as I remember, or I know. Wait, it was discussed. Have we mentioned the bars with expansion gaps, or not really?
Yeah, you were talking about it.
Okay, so only a brief revision. So the possibility to reduce stress is to provide a thermal gap. So this is the case here when in one of the elements there is a gap. So they are connected via a pin, but there is a gap. What it means that if the bars are differently heated, or they deform differently by means of temperature change, to some extent they can deform without any stress. So they are really not in contact. We can determine here as such a gap size, the critical gap size, which is exactly the gap size when the materials come in contact. So if there are such parameters for given, so let's say there are deformations for material number 1, for object number 1 and object number 2, this is the critical gap size. So this is the gap size when they do not come in contact. So that would be the magnitude when they do not come in contact. So if delta, actual delta, so actual gap size between these two objects is bigger than the critical, we have no contact at all during the entire process. and stress will be 0. The objects will only deform, but independently, so they will not come in contact and they will not exert action on each other. So there will be no action interaction between these two members. If the gap is smaller, they will come in contact, and of course we have plus or minus sign depending on in which direction we go. So whether we increase or decrease whether we close the gap on the left-hand side or on the right-hand side of the connection. And we also discussed how to determine elongation, stresses, and so on and so forth. And this was the end as far as I remember. We discussed here the issue. We finished at the issue that there is no external load applied, so we have only the situation. There is a force interaction between these two members, so they come into contact, so they cannot deform freely anymore. So we cancel the gap, and there is a contact. So from the on the basis of the equation of equilibrium, we have only here two forces, one resulting from the member number one and the other on the member number 2. They are in opposite directions and they have to cancel out. So the sum of these two forces is 0. Force can be represented as stress in a body times its cross-sectional area. So this is the resultant force in the section. The same for the second one. And using this information from previous slides, we can find out the total elongation of the system, which of course depends again on these on such factors. So rigidity or stiffness of member times elongation, thermal elongation of member number 1. This is for member number 2. And again, in the bottom, in the denominator, we have the same factor, EA over L. This is one thing. Here is the other object, the other factor, where we have the gap involved, the gap between these two factors. So this exactly object releases or decreases the total elongation of the system. And stresses can be calculated in the same way. So they generally the introduction of the gap generally decreases stress within such a connection, comparing to the situation when no gap is present. So if there is no gap, there would be only these two factors, and here we counteract this thermal deformations and the stress that occur from here. And there was an example to be discussed. We have two stainless steel pipes. They are the parameters of the steel. So alpha is 14.8 times 10 to the minus 6 power, 1 over K. The Young's modulus is 198 gigapascal. We know that both pipes are of 5 meter long and are concentric. So this is the situation shown here. We have internal pipe and external pipe, so a shield. and they are attached at the ends. The inner pipe is a 100 millimeter nominal pipe. So we have its exact dimensions. So external parameters. What's going on? Okay, external diameter is 114.3 and wall thickness is 305. And we have the outer pipe, which is the number 2 here. And this is 150 millimeter nominal pipe, so we have appropriate dimensions of the exact dimensions of the pipe. And both pipes are initially stress-free at temperature 20 degrees Celsius. So someone has switched on the microphone and I'm hearing some noise. So please mute yourself. Both pipes, as I said, are at stress-free conditions when the temperature for both of them is 20 degrees. So this temperature, this is, let's say, the initial state is 20 degrees, so no stress occurs. So they are perfectly fitted between these two, let's say, connections. And then the outer pipe is warmed to 25 degrees Celsius. So only by 5 degrees. And the inner is cooled to minus 180 degrees Celsius. So let's say it's a cryogenic system. We transfer here cryogenic fluid here. So it is cooled down by 200 degrees Celsius, okay? Or 200 K. The question is, what should be the expansion gap in the inner pipe to limit the thermal stress to 130 megapascal. So this is the situation here now shown, that we have a gap between these two pipes. This is the situation because if we will cool down the internal pipe, it will get shorter. So it will try to compress the external pipe. The external is only by 5 degrees warm, so there is almost no change. But huge change in the length in the internal pipe, so shrinkage of the internal pipe will produce compressive force on the external pipe. So they will come into contact and they will exert forces on each other. We have to determine what should be the magnitude of the gap to reduce the stresses to the allowable limit. So we need some geometry data. We have A1, so the cross-sectional area of pipe number 1 and pipe number 2. There are such factors as I told you in the formulas: E1, A1, L2, E2, A2, L1. Since both are of the same material and the same length, so Young's modulus and length cancels out. And we have here this is the ratio of the areas. It should be, of course, equal, not minus. Okay, so if no gap is used, so this is the situation, we have no gap. So these pipes are connected together, are fixed ends. So the formula is very easy, and the result is terrifying. Look at this. If there is no possibility to any free deformation, the stress would be destroying for the system. 3,740 megapascal. Let's assume that I think the steel, the allowable stress for the steel is, or the ultimate stress is not bigger than, let's say, 400 megapascal. That's it. So we have 8-9 times more stress that it can survive. So it would be for sure destroyed. So we see that there is a necessary to introduce the gap to reduce the stress. So we have delta T1, so the internal pipe is cooled by by 200 degrees Celsius, and the upper one is heated up by 5 degrees Celsius. So stress 1 and the internal pipe, on the basis of the formula which was discussed before, is determined on the Young's modulus, the formation of the entire object divided by the original length, of course, and increase in temperature of the first object minus the gap when they come into contact. So we can calculate here we have the same factor, the same component. So if we solve it for this chain, for this factor, so this is delta L0, so total deformation, total elongation of the object minus the delta, so the gap required divided by L is sigma over E plus alpha T1. We know that sigma should be kept at the level 130, so no bigger than that. So let's assume we are calculating what is the required gap to have the stress on this level. Of course, if the gap will be bigger, the stress will also be lower. So this factor, the delta L0 minus delta over L, is that much. If we introduce all the data, it's minus 2.3 times 10 to the minus third power. And this is, of course, unitless, because here we have length and here we have length. So this is a factor, of course, of the deformation when they come in contact, exactly, because this is delta 0, so the total deformation minus the gap which is there. So from here, on the other hand, delta, this factor can be calculated as, this is the total elongation, delta L0, as you know from previous slides, alpha times A delta T1 plus A2 delta T2 divided by the total cross section minus delta over L. So we can go to calculate, solve it for the magnitude of delta, and it will be expressed by solution of the former formula to get the actual number of data, and if we put all the information there, so the material data, the dimensions, and so on, we'll get that the gap should be close to 2 millimeters. So if it will be 2 millimeters, we'll have stress on the basis on the level of 130 megapascal. If the stress is bigger, that would be lower. Sorry. Here we have also calculated the critical size. So what should be the gap that the two pipes do not come into contact? So it would be 15, something like 15 millimeters. We have only 2 millimeters. So look at this. That much would be zero stress. But if we reduce only the gap to 2 millimeters, the stress will be on the level of about 130 megapascals. Okay, and stress in the second, so we know that they come in contact, so the gap that would provide no contact would be 15. We have only 2. So delta is lower than the critical size. So there is an interaction. So this is the case which was discussed in the end. So these 2 forces are counteracting balance. So this is force in member number 1, so in the internal pipe, and this is the force in external pipe. We know what's going on in the internal pipe because the stress is calculated to be 130 on the basis of the gap. So we can calculate what happens in the second one. So it is the stress resulting from such a condition will be less than 80 megapascal of compressive. So minus sign means that there is a compressive stress in the external pipe. So looking at the picture once more, this is the situation. If this internal pipe shrinks and we obtain here 130 megapascal of stress, look at the or once more at the direction of stresses. If this once shrinks, so it is shorter, they come into contact, and the inner pipe tries to compress the outer pipe, and the outer pipe tries to extend the internal pipe. So that's why in the internal pipe we have positive stress, so tensile stress, while in the outer pipe, the external pipe, we have compression. So the compression would be slightly less than 80 megapascal of compressive stress. Okay, so we can proceed. And the other possibility, again, to release the stresses, the mutual interaction between objects, between bars in contact, bars in parallel or bars in contact, is to introduce the spring element. So this is schematically shown here as a spring put between the connection of these two bars. So exactly, we have a situation that they are in series. The spring is in series with the bar. So we have such a situation that they can have different lengths. They are heated up by different amount. They can be of different material, and they are connected here by a rigid plate. They can be also by force applied at the end, but between one of the members here, the bar number 1, and the connection surface, there is a spring introduced of given constant K as P. So of course the entire increase or change in length of the entire system, so measured here at the end at the plate, is change in length of member number 1 plus change in length of the spring. On the other hand, And from here, we can say that the change in length of spring, it is the result of the dependence on the, you know, that the force in spring is equal to K times the elongation. Okay, delta L. So okay. So the elongation of the spring, or change in length of the spring, because it not necessarily is elongation, can be shortage. So it's F1. So force in the F1 is a force in the spring divided by K spring. And this is force which is generated in the upper one system as, of course, sigma A1. It could be forces, of course, sigma times A divided by K spring. This is one of the factors. The second one, the delta L2, so elongation of the lower object, is elongation due to force applied. So this is sigma over E times L, and elongation provided by the change in temperature. And that will be also the delta L0, because there is the attached delta L0 is exactly measured on the end of the L2. So delta L2 and delta L0 is the same. Here, delta L0 consists of elongation of the member plus elongation of the spring. If we join them together, delta L1 is, of course, the force generated. So that what happens in with the member number 1. So it's change in length is force generated, and the force really comes from the spring applied, and elongation due to change in temperature. So the first thing is delta L0. So we have total delta L0 minus the force from the spring. Elongation resulted from the change in spring length. So from here, delta L0 can be calculated as sigma 1 A1. So force in member number 1, and the same, this is the force which is in the spring. And we have here factors that resulted from the, let's say, susceptibility to deformation of the spring. So this is 1 over K. And the same factor somehow calculated for the member for the bar. Of course, deformations here and here are completely different. This is quite elastic, this is quite stiff. But we have two factors, so we have exactly two elastic elements connected in series. So we add up their stiffness in such a way, 1 over K. All right. So the K for bar for such an object is EA over L. So we have a reciprocal of the of this factor, and this is the part connected with the temperature change. If we look at what happens at the plate of the rigid plate at the end of the system, we can have three forces. At least two are there. So F1 and F2. but there can be also force F applied from outside. So F can be 0, or there can be some force applied from outside. So external force can be there. In general case, F1 and F2 can be expressed as stress times cross-sectional area. So this is what happens in bar number 1. This is what happens in bar number 2. And some of these forces, so the condition of equilibrium, can be represented in such a way. So we are generally looking for stresses. That's why we express them as stresses. These forces are expressed as stresses. So delta is 0. If we put the data there, connect all the factors together, we can determine the delta as 0. So increase or change in length of the system in such a way seems to be not very user-friendly, but it's not that bad as it looks at the first sight. So here we have, let's look at this. This is the elongation of member number 1. This is elongation, thermal elongation of member number 2. And there is a sum of, let's say, the reciprocal of the stiffness, or the constant, stiffness constant for these two, the upper one system, so bar with spring, and this is the same story for the lower system. There is only bar, okay, and this is divided by the again the let's say elasticity or the rigidity of the system. If there is external force, we have added here external force. If there was no force, F is just 0. So, and then we can from here check how the elasticity or the spring constant can affect the stresses in this system. It can be shown also in such a form. We can express it by such factors, Ka and can be. So write it down more generally. So this is the relative or the epsilon of factor of member number 1. So this is the strain, thermal strain of member number 1, where the factors are Ka, Kb, and Kc. So this is, let's say, compressed somehow to have it more user-friendly than the previous formula. So we can determine Ka as this factor, Kb as this factor, and Kc is Ka plus the ratio of lengths. So this is the same as previously, but let's say expressed in less terrifying way. So sigma in the member number 2 is calculated in the same way as previously. Sigma 1 is expressed by the factor K2. It is here the spring factor is involved in Kb. If you look here, we have K spring. Sorry, K spring is here, and a K factor, the second factor. And from the equation of equilibrium, it is the sigma 1 expressed in such a way. It's of course equal to force in member number 2 and the force in resulting from the external action. Now, if K spring tends to 0, so the spring, if the constant is close to 0 or approaches 0, it means that there is almost nothing. So it exerts no force. So it's very, very elastic spring. So it generally exerts no force. In such a situation, we would have that there is no stress. So it looks like these bars are not connected to each other almost. And at least in bar number 1, stress approaches to 0. Because this factor, we have such a factor, if this reaches 0, this factor is very, very big. And whatever it is, if this is very infinitely big, f sigma 1 approaches 0. And if there is no force from exterior, member 2 has also 0 stress. If the force is present, stress in the member number 2 results only from the force applied from the exterior. So if there is a force from exterior, stress in the member number 2, so the directly connected to the wall. So you see the situation here. If we have very weak spring, so it exerts almost no pressure, there is a gap and the members do not come into contact. So stress in this member, so this member, the members exactly, both bars, that they can deform almost independently and they are unconstrained. So in such a situation, there is no stress inside. And the only stress that can occur in the lower bar results only from this force. So this is the magnitude of the force will be responsible for stresses. If there is no external force, the stress in the second member will also be 0. Okay, and an example, we have a vacuum jacketed transfer line. So again, pipe in a pipe for liquid oxygen, and which consists of 2 concentric pipes. The outer line is again 150 millimeter and the inner is 100 millimeter nominal pipe. So very similar case as it was before. The connection is slightly different. The entire length of the system is 12 meters, so it's longer than previously. The outer line is 12 meter and the inner is 20 centimeters longer, because there is a, let's say, expansion system applied. The system is free of stresses when the temperature is 20 degrees Celsius. So if both materials, both pipes are at 20 degrees Celsius, there is no stress in the system. Under operating conditions, the temperature of the inner line is minus 180. So the situation as it was in the previous example. And the outer line is 30 degrees Celsius. Its temperature is 30 degrees Celsius. So quite similar story as before. Both lines are constructed of stainless steel with given parameters, same parameters as before. We want to limit the stresses in the system of 16 megapascals. So before it was 130 in the pipe. Now we don't want to have more than 16 megapascal. We want to obtain it with a thing that is the bellows. So a spring element, elastic element at the pipe. So this is the case. This is the cross section This is the bellows shown. So this is a elastic element. So we have external pipe, internal pipe. The internal pipe is longer by 20 centimeters. So there is a 20 centimeters between them. And here there is an elastic element placed, so such bellows. The elastic elements plays the same role as spring. And we should calculate what should be the K spring, so the spring constant of the bellows, that stresses occurring due to mutual interaction between these two pipes is no bigger than 16 megapascal. Of course, we'll use the formulas which were discussed a minute before. We have all the information here about the geometry, about the material. You have to use the formula to determine the necessary Ka spring to reduce stresses. So we know also the result, what is the result in stress, and we want to know what should be the constant, the spring constant for the bellows, which is mounted here. So the spring element, you probably saw such solutions at different piping systems. So we have from the equation of equilibrium, we have no external force. So force generated in one member is equal to the force generated by the second member. So we have exactly F1 equals F2. So this is the force in one member, and this is the force in the second member. The pipes, of course. And we know that there should be no more than 60 megapascal. We have a ratio of stresses. A ratio of cross-sectional areas of these pipes. So if the external pipe is 16 megapascal, so in the internal will be less than 10 megapascals. This is the amount of stress, or the magnitude of stress that we occur. This is I assume this is the maximum stress which is allowed in one member, in the more stressed member, in the more stressed pipe. So in the second one, we'll get 9.7 millimeters. And now we have to determine at such stress levels what should be the K spring. This is the only unknown quantity that emerges here. So the elongation of the system, or change in length of the system, can be calculated on the basis of initial length, on the stress generated, and on the basis of the material data and change in temperature, as we have this formula in the previous slides. And it turns out that if the member is, the internal pipe is cooled by 200 K, so from plus 20 to minus 180, it will shrink by 35 millimeters. So you see that even if the external pipe would not change temperature, they will come in contact, because the external pipe would remain, the difference between these two pipes is 20 millimeters only. I know, sorry, there is more, this 20 centimeters, and here we have only 35 millimeters. But we have a connection between them via a spring element. Delta is 0. Looking at this is calculated from the internal pipe, from the external point of view. We have a K-spring there, so the spring element. We know the stress there because we have calculated the stress in the external pipe. We know its cross-sectional area. We have all the geometry known. And we know what is the total elongation of the system calculated on the basis of the second of the internal pipe, which changes the length, shrinks, and this change in the external pipe. So we know to what extent that one shrinked. So how far moved the connection. Looking at the external pipe, we know that its change in length of the external system consists of change in length of the pipe and change in length of the, let's say, the bellows, so the spring element here. So this is the change in length of the external system, so change in length of the pipe and change in length due to the spring element. So we can calculate, introducing all the data, that 1 over K spring is 0.0022. So K spring is 454.5 newtons per millimeter. This is the spring constant that is required to have stresses in both elements not bigger than 16 megapascal, and we know that in internal is 16, so the external is only less than 10. KB will be the factor KB will be 65. If introduce all the data, so sigma 1 calculated in this manner, in the same manner. So this is a, let's say, checking calculations, and we of course obtain the same result as we assumed. So which means that we have calculated this correctly. So the external pipe is compressed by only 9.7 megapascal. And this is the result of the force generated by the bellows, so by the spring element compressed by 35 millimeters, more or less, something like this. F1, so force in the pipe number 1 will be 17 kilonewtons, and change in length in the spring would be, in such a case, 37.5 millimeters. Okay, so it consists on the on this 35 millimeters of shrinkage of the internal pipe and some elongation, so by 2 millimeters elongation of the external pipe due to heating up by 10 degrees Celsius. They are quite long, so only increase in 2 millimeters provides heating up by 10 degrees only provides elongation by 2 millimeters, more or less. Okay, so we see to what extent we can reduce stresses by introduction of either spring element or thermal gap. This bellows, of course, if we would provide here a thermal gap, there would be a leakage. So there would be, let's say, a heat loss in such a case. If we cover it with bellows, we also we generate, let's say, a cover for the system, for the internal pipe, not to lose heat from the system. So this can be more convenient. But if there is possibility to introduce a thermal gap, that's easier and cheaper to solve the problem. Okay, and now let's move further to next topic, which is a variation in temperature now, because previously each case calculated it was assumed that the stress, sorry, not stress, but temperature is uniform in the body. So we increased or decreased the temperature, so we changed the temperature, but uniformly. So all the time in a body, any one of them, the temperature was equal inside the body. In each point that was the same. Now we'll discuss how the temperature variation can affect stresses and what will happen in such cases. So firstly, we'll discuss the variation in lengthwise direction. So we'll discuss members, again, straight bars only, but we have now situation that temperature in a bar along its length changes. So the delta T, so change in temperature, is a function of x. And each location, of course, we start with let's say stress-free condition, so initial state, everywhere is T0, and then we increase temperature or decrease temperature, whatever, we change temperature, but it is not in the same way in the entire object, rather than it is different at different locations in the body. How will it result in the behavior of the object? If we take an infinitesimal part of the material, so we have two sections, let's say it's very, very thin slice of the material, and we see that there is a change, the colors show a change in temperature. And if we take into account very thin slice of material, this is from the mathematical point of view infinitesimally small, Tx, and we add any location from at the material, this part will due to heating up move by U. So this part extended from 0 to x, so this piece of material extended by U due to change in temperature. But if we look here, now we look at that much of material. So slightly longer piece of material. The previous one was x, and now we have x plus dx. Of course, only slightly more, but this piece of material also extends, so the elongation will be bigger. Of course, only slightly more bigger, but there is a change due to elongation of the small slice of material. So on the next section, so one end of the slice will move by U, the other will move by U plus d over dx times dx. So we observe elongation of the thin slice of material. This results just from the observation of what happens. So elongation of the right-hand side and elongation of the left-hand side and of the material results of du over dx. And this you should remember from your strength of material course. So this is the linear strain, so relative elongation of a material, and it is exactly equal to change in length of the small size divided by the original length. So this is just a deformation of an element of the material. If we look back at the stress strain temperature relationship, so if we had only mechanical part, it was that one. Last time we introduced also the second part, the thermal part. So the elongation is provided due to mechanical action, so force if there is any, and temperature change. And this is du over dx. So this is the elongation of a elementary piece of material. If we look at the equilibrium of the bar element, so this very thin slice of material again, we have on left-hand side, we have force, which is determined as sigma A, so stress times cross-sectional area. On the other hand side, there may be a slightly different loading, so a slightly different force, sigma plus d sigma, so a little bit different. If you combine them together, if you have no external loading, there is no external loading, this means that d sigma over dx is 0, so sigma would be 0 in such a case. So you if we calculate the here we have this formula, epsilon is du over dx, so u is epsilon dx. So u is sigma over e times x, and we have to integrate it due to change in temperature, because temperature is not constant. Previously temperature was constant, so the rise in temperature was the same in the entire object. We had only alpha times dt. Now, since the temperature is different, we have to integrate it over the entire length of the object up to the location where we want to calculate stresses. So we have to integrate the function of temperature rise due to its change in length. So if constant, we have only delta t, alpha delta t times L. That would be all. If the temperature changes, we have to integrate it. Very often, alpha can be kept as constant, so it makes the integration slightly easier. So we can take the alpha out of the integral, so we only integrate the function of temperature change. If the alpha is a function of temperature, unfortunately, we have to integrate it as a product of two different functions. In such a case, we can get rid of the delta alpha out of the integral. So at the end, so the total elongation of the member with variation in temperature along the bar. So the elongation observed at the end, at the right-hand side, let's say we have on the left-hand side, we have fixed the object and it can extend to the right. The total elongation will be sigma over E times L, so x equals L. And there's an integral from 0 to L of the delta t. And delta t, we can substitute this integral. If you integrate it, you will obtain an 1 over L integral of 0 to L delta t. And this is an, let's say, integral average of temperature. So instead of writing the integral here, you can take as average temperature, integral average temperature in the object. So it changes with x, but instead of taking the integrating, you can firstly calculate the average temperature in the bar and calculate it in the same manner. If you look back to the notes from previous lecture, from our previous meeting, this is exactly the same what was before with the uniform temperature change. But instead of delta T, which was the same at every point within the material, we have here now the average in the material. So, but the shape of the formula is exactly the same. So here we have the temperature averaged along the length of the object. Epsilon, so in the strain which is observed is of course U over L. So change in length divided by the original length. And this is of course sigma over E plus alpha delta T average. And as you see, this expression is exactly the same in form, of course, as the expression for uniform temperature change. As I told you a little bit before, a minute before, that instead of constant temperature, you have an average temperature along the length. So shape of the function is exactly the same. Different amount, different quantity is introduced into the temperature rise. So let's look at an example again. We have a steel rod whose parameters are given, so alpha and E, with diameter of 6 millimeters and length of 300 millimeters. And it is mounted between two rigid walls. We know that at 25 degrees Celsius, the rod is in a stress-free conditions, which means it is fitted exactly between the walls. So if there is no interaction, no force is exerted from the walls on the bar or opposite. We have to find stresses in the rod and the elongation if its ends are maintained in the following temperatures. The left-hand side end is 25 degrees Celsius, so for x equal to 0. The right-hand side end is 95 degrees Celsius, so for x equal L. You can calculate from here the temperature distribution along its length as a linear one. So it's a T0 plus T1 minus T0 times x over L. This is, of course, the solution also you will get as you solve the heat equation for the heat transfer analysis. So let's look at our solution. Firstly, we know that we can use the simple formula as it was for uniform temperature increase, but we have to substitute the temperature rise or temperature change by means of the average temperature. So let's calculate first the temperature, the average temperature of the bar. So, you know, it's 1 over L integral of the function t minus t0 x over L dx. So this is the, if we calculate it, it will be half of T1 minus T0. So this is the average temperature in the material, which if you introduce data, it will be 35 degrees. So we rise the temperature by average of 35 degrees Celsius. This is the original case. Okay, and now we can use the simple formulas which were already introduced before and now reused. If we have the fixed ends, because the question was what are we to calculate? Find the stress in the rod. If the and the elongation, if the ends are fixed in fixed temperature. So this is the case when the ends are fixed. So we have 0 increase in temperature. The stress in such a case would be, there is no external loading, no force, nothing else. So we have only this this factor connected with temperature rise. So it will be minus alpha E delta T average. If we introduce the data, we'll obtain that this is almost 84 megapascals of a compressive stress if it was fixed. So there's the average rise in temperature as 35 degrees Celsius of the 300 millimeter long bar, and it would result in 84 megapascals of compressive stress. If the ends are free, the bar would extend. We can calculate the strain U over L. This is again a constant parameter, 0 stress, and we have alpha over L and the average temperature. If we integrate it, there is a x over L. So if we integrate it, is half of x squared over L. So the integration is quite simple. So the stress is minus alpha E delta the average. So U over L would be expressed with this formula. You see a quadratic formula. And if we introduce data, U over U as a function of X divided by 300. So if we multiply it with 300, it goes on the right. This solution would be like here. So here you see the deformation of the object. So displacement of the object observed at different locations. At the ends, it's fixed. So there is no possibility to move anywhere. So the displacement at the ends are 0, but the highest displacements are in the middle observed, and this is less than 0.03 millimeters. So it's expressed in millimeters. So such deformations will be observed if we have non-uniform temperature distribution. If the temperature distribution is uniform, so the temperature rises in the same way over the entire object, we'll have zero deformation. Zero, U would be zero all the time. But if the temperature rises at different rate at different locations, in other words, the higher we are, the further we are on the right here, the bigger the bigger the temperature rise. And there is, of course, a mutual interaction between over the entire length of the rod. But we will observe the highest deformation. Of course, they are quite small, but we will observe deformations here, rising, reaching extremum, so maximum, and falling down, and the deformations at the end, at both ends, since the ends are fixed, is completely zero. Okay, so you see the difference when we have a system when the temperature is uniform and the system when the temperature changes along the length of the material. Now we'll discuss the temperature variation across the cross section. I think since we are close to 3:30, we can make a break now, and this issue will be discussed after the break. So about 15 minutes break. So at 22:04 we'll meet again. Okay, we can continue. The second kind of variation of temperature. This is the variation across the section. You hear me, yes?
Yes.
Okay. So formerly we have a longitudinal change in temperature, longitudinal. With a coordinate x, so along the axis, and now we'll look what happens if the temperature varies in a lateral direction, perpendicular direction to the axis. We will assume now that along the length, so along the x-axis, we have uniform temperature. So at each, let's say, distance from the center, along the x-axis is the same temperature. We only see a variation in the vertical direction, so in the y direction. We will discuss now a case where the temperature distribution is symmetrical. So the axis of symmetry is x, and we have the same temperature at the same distance from the axis of symmetry. So let's say 5 millimeters above and 5 millimeters below the axis, we have exactly the same temperature. So this temperature distribution is symmetric without the along the centroidal axis. If the cross section is symmetrical, of course the axis passes through the center of the object. There can be a force applied there, so a mechanical loading, but that symmetrical distribution of stress, symmetrical distribution of temperature results in such a distribution of stresses. So they are, if inside is higher temperature than at the sides, we have such a parabolic, let's say, distribution of stresses. The symmetrical temperature distribution results in, let's say, total force generated here is 0. So the integral of stress over the entire area is equal to 0. So, or let's say a moment, this is, let's say, not exactly a stress, this is a force generated by the temperature change times distance from A. So this is exactly a moment, bending moment, which is generated. And if it's calculated through the center, part of the material tends to extend in this direction, part tends to act in the same direction, but they are on the opposite side of the center, so they cancel out. So the moment generated is 0. In other words, the object will not bend, so will not be curved. We only see such a distribution of stresses, so they will be different at different locations at the cross section, but along the x-axis, everything will be the same. If we apply the equilibrium condition, so F must equal to the integral of sigma, of course, over dA. So in total, this is the internal loading generated by the thermal forces inside, so the thermal expansion. If you recall the formula for epsilon, so elongation of a system. It's, of course, the elongation due to mechanical loading. Now, this is the strain, yes. The strain due to a mechanical loading, so Hooke's law, and plus the thermal elongation. So if we calculate stress from here and put it there, it will look like this. So the force will be equal to integral of E epsilon 0 dA and integral of alpha E delta T dA. So two factors, just changes in the in the formulas. And this factor, we will call it a thermal force, and it will be denoted by letter F T with index T, so which means that this is a thermal force. This is, let's say, a force generated by the deformation of the body. And this is due to a different deformation of different parts of the body. So going further, we can write it as F plus Ft. So mechanical force plus thermal force is epsilon 0, which is constant if the temperature distribution is symmetrical over the height of the material. Epsilon is 0. Sorry, not 0. Epsilon 0 is constant, is same in each location across the height. So we have an integral of E. Usually it is constant. So E0 epsilon 0, so the total strain of the material of the ball is mechanical force plus thermal force divided by the flexural this rigidity of the material. So E times A, Young's modulus times cross-sectional area. Looking back, if E is independent on temperature and alpha is independent on temperature, we are looking at this formula here, Ft. So we have here alpha E. Delta T, as we know already, is dependent on the location, but it's symmetrical. But there are two parameters, two material parameters, and if these two parameters are independent on temperature, they can be extracted from the integral, so they are out of the integral. So we have alpha E integral of delta T dA, and this is nothing else as an mean temperature across the cross section. So the mean temperature is calculated exactly as 1 over A integral of delta T dA. So again, the integral average integral mean temperature across the section. It does not depend on X. So in each section, no matter where we are along the material, along the object, is the same mean temperature. So we can calculate the thermal force generated by the temperature rise or temperature drop as alpha E delta Tm, so the mean temperature across the section. And resulting stresses, which is the function of y, so in the vertical direction, then k vary. One more thing, y starts here, so this is 0y. There is a positive y, negative y. So you see it spreads from 0 to half of height and minus half of height. So we have E times epsilon 0 and the thermal part alpha E delta t as a function of y. This is shown that this is a function of position in the vertical direction. And it can be written as F over A, so the external force divided by cross-sectional area. And we have alpha E, and there's the rise of temperature, delta Tm minus delta. So average temperature minus change in temperature of the along the in the cross section as a function of direction perpendicular to the axis of the bar. And this is the stress distribution away from the ends of the bar. There's such a note. Why away? Because you see that the stress will depend on the location. Will depend on the location perpendicular to the surface. So if we, I'll try to draw it somehow. If we have, let's say, the bar, this is the, let's say, end of the bar. And we have different temperature, as you saw, and the distribution, let's say this is the stress distribution. It was more like this. Oh, I should be here. So you see that there is a different, there is different, there is different. So the distribution is it is not uniform. So if we are close to the place where the object is fixed, there is a interaction. So the between the object and the surface, and we can use this formula. It will be true if we are away from the, let's say, application point, where the contact point, where according to the Saint-Venant principle, so we should be at least about the distance, let's say the distance height from, let's say if this is high h, we should be, this is true if we are about 1.5 h away from the support. The distribution given by this formula will be okay. If we are close, this is not the story. So the disturbance from the locations of the influence of the surface, the surface on the stress distribution is quite significant, and it will be disturbed at the locations where the force is applied or where the support is applied. So we should think that this is more or less the distribution of stresses, but inside the material, within the material, the ends are somehow disturbed by means of the side effects. If the bar is unconstrained, so there is no interaction between walls, there is no external force, nothing. So there is only Ft observed. So F is 0. So Ft is given like that. So this a recollection of this what was before. So the strain observed in the bar is just Ft, so the force produced by the system, by the temperature change, and the rigidity of the system, so E times A. And this is, of course, looking at the formula E alpha E delta T M. Not really. Not really, because yes, the A will result from from this force, and this is not here. It should be cancelled out. No, there is no E. It is cancelled, and we have to calculate, and there is A missing, so I have to correct it, because after integration we also have here A, and we have alpha E delta Tm times A as we integrate over the entire area, and this is divided here by EA, so we have only alpha delta Tm. And of course, for general system, uniformly heated or cooled, the formula is exactly the same. So epsilon is alpha delta T, but if uniform, there's only one delta T equal everywhere. Here we have the mean temperature across the section, and the stress distribution resulting from here would be minus alpha E, and the change in temperature delta T as a function of location across the section minus the mean temperature in the cross section. And we can say, look at this, there is no constraint, nothing acts on the body from exterior, but we observe here stresses, and the stress is as a function of y. And although there are no external constraints which generally produce reactions and they act as forces on our body, we observe here, let's say, internal constraints. Why they are so? Because the outer surface and the inner region try to deform in a different rate. Let's say the external part tends to extend more than the internal part, so the difference in the expansion will result in stresses. So there is a conflict between different parts of the material. So although there are no external forces, no external loads, nothing like this, we will observe thermal stresses. This is exactly the case that such thing can occur if the temperature distribution is observed in material. So there is no uniform temperature, rather than there is a distribution, uneven distribution of stresses across the section, and some parts deform in a different way than the other parts. Of course, this is the case when we have symmetric temperature distribution with respect to the central line, so the centroid. There will be slightly different story if the temperature distribution is not symmetric. A bending will occur in such a situation, but we'll discuss it in a moment. So this is the reason. The distribution of stresses, distribution of temperature inside the body will result in thermal stress as well, even if there are no external constraints. Example, we have a rectangular iconal bar, the parameters given, which has a thickness of 30 millimeters, so the height of 30 millimeters, and length 450 millimeters. Both ends are rigidly fixed. And we observe, due to some effects, so energy dissipation, a symmetrical temperature distribution within the bar, which is given by this formula Ts plus Tc minus Ts, and there is a function of y, where Ts is the surface temperature of the bar, and Tc is the center temperature of the bar. As you have it shown here, more or less, with the colors. So it's hotter here because the inner temperature is 60 degrees, colder at the sides, so it's 30 degrees. And we have to determine the stresses or stress distribution in the bar and the resultant force at the ends of the bar if such temperatures are reached. The system is at stress-free conditions if the temperature is 20 degrees Celsius. So let's try to use these formulas and observe what happens, how the temperature distribution will affect our system and the stresses which are generated there. So the temperature change from the stress-free conditions. Stress-free condition is everything everywhere is 20 degrees Celsius. And now we rise the temperature and we see that at the ends, at the sides, at the surface, there is 30 degrees Celsius and inside is 60. So it can be written like this. So delta Ts, increase in temperature, which is in this case, 10 temperatures, 10 degrees Celsius, from the initial stress-free temperature to the end temperature, let's say, and the distribution between surface and the center is Tc minus Ts, 1 minus 2y over h, where y is measured from the center. Upward is positive y, downward is negative y. That is divided by h. The mean temperature change in the cross-section as delta Tm is 1 over h, and we integrate it from minus half of h up to half of h. So from here to here. And this is as the delta T, which is a function of y. If we introduce the formula for temperature change and integrate it, it's quite easy because this factor is constant. This is a constant factor, and we have only here y squared. So after the integration, in the bracket there is a y over h minus 4y to the third power over 3h to the third power. If we put the boundaries in, the result will be delta Ts, so change in temperature of the surface, plus 2/3 Tc minus Ts. So from here we can easily calculate the mean temperature across the section. If the bar is constrained, and this is the case, we will not observe any deformation, so any extension or compression. So epsilon 0 is 0 due to the walls that constrain the movement. So sigma is equal, as you may recall from several slides back, minus alpha E delta T as a function of y. And of course, we introduce here this function, so the mean temperature here, the temperature here. So the distribution of stress, if we put the data, we have a squared function of y, as you see here. So it looks like the stress distribution will be a parabolic function of location and the cross section, so along the lateral direction. So if you do the computations, it will be more or less like this, minus 2.795 times 40 minus 215 y squared. So once more the same. If we draw it, it will look like this. This is our bar. This is the center line. So the highest temperature here in the center. And here we have the distribution of stress. If you put the data here, you will observe that for y equal to 0, this is 0, so you have minus 2.7795 times 14. So this is 111.8 megapascal in the center. So for y equal to 0, it's here. And then it changes quadratically if you are away from the center. For y equal half of h, it will be about 28 megapascal. So here we have 28, here we have 111.8 in the center. And the distribution is quadratic, as shown here. So you see that there is no equal stress in the section. Of course, different stress will result in different strains, okay, here. And of course, there is a interaction between the areas. This area would like to extend more than that one. That's why we observe stress distribution in this object. And the force, the thermal force, which reacts on the walls, would be from the stress distribution, resulting from the temperature distribution, it would be about 100 kilonewtons. So this is the constraint bar. Okay, as you remember, if there was uniform temperature, the stress was equal everywhere at each section, was the same, because delta T was not dependent on temperature, on location. Now it depends on the vertical direction, so that's why we observe the stress distribution, different stress distribution in the object. Of course, if the inner part was colder and the outer was hotter, it will be reversed. This distribution would be reversed. If the system was unconstrained, so what was free, we can imagine the situation which was observed with the concentric pipes connected together, as we discussed in our previous case, in our previous part of the lecture. So in this case, the internal part tends to extend more. It is constrained by the external part. So this extension would produce positive stresses, so tensile stresses close to the surface, and the external part would produce compressive stresses inside the material. So that would be the distribution, the difference. So there would be a different signs in this in distributions of stress in the material. Okay. We'll start. I don't know how far we'll go today. One more thing I'd like to mention. So thermal bending. So this is the situation now, similar to what we discussed a minute before, but the problem is now that the distribution of temperature is unsymmetric. So it is not symmetrical. For example, here is colder than upwards. So this is our beam, the object, and we observe that the temperature distribution depends on the vertical direction. So it's colder here and hotter here. So this upper part would tend to extend more than the lower part. Of course, if the temperature was uniform, it would extend by epsilon 0 times L. Of course, we have to assume here some things that are necessary for the discussion to be true, which are usually resulting from the strength of material approach, which was discussed on your studies. So first, we say that all cross-section planes remains plane after bending. So we can say that if the lower part deforms less than the upper part, for example, this object should bend. So it should be curved after deformation. So we assume that after the curvature, so let's say it's curved like this, each section, anywhere it was, previously it was, let's say, vertical. Now it is at some angle, but as it was plane, it is still plane. It is true if the deformations are small, and we are discussing only such cases. So small deformations where we are within the Hooke's law region, so stresses are not bigger, we do not enter into the plastic area or elastoplastic deformation. We have the beam relatively narrow, which means that the lateral contraction or the lateral expansion, which results from the Poisson's effect, of course, as you may recall, are negligible. So this object is quite thin. And the longitudinal axis of the beam is straight initially. So these are the main issues we have to mention here before we discuss it any further. If you look at the formation, the strain, again we recall the same story over and over again. So the strain in the material of the object is, of course, the mechanical strain resulting from sigma over E, and strain resulting from thermal deformation or thermal expansion or contraction. And we can say that we have here E0, which is the mechanical part of the deformation of the strain, so due to the mechanical effects which are applied usually to the beam, so moments or forces, lateral forces applied, and the bending effect resulting from temperature distribution. So linear strain and bending strain. You see what happens here, and this is the end, of course, highly exaggerated. So we can observe that the linear strain due to, let's say, extension of the material and combination of a rotation. So two effects are combined together, extension and rotational due to the bending, due to the curvature of the beam. So UB can be observed here as epsilon B times the length of the material. We can also draw here some conclusions, some geometric conclusions, that the tangent of the surface, of the end surface here, the end section, to the, let's say, original position, so from to the vertical, as it was here before, can be expressed as tangent of the angle phi. Since the angle is small, we are dealing with very small deformations. So tangent of a very small angle expressed in radians, of course, is equal to the angle itself expressed in radians. You can check on your calculator if you want, not in degrees, but only in radians. And that would be epsilon B times L divided by Y. So this can be resulted from the small here angle, from this triangle here. And also it can be expressed as L over R. So length over the radius of the curvature. So it is exactly the same, can be expressed also in this form. If we combine them together, so these two expressions can be combined together, so we will connect LR and the location on the section. So epsilon B would be Y over R. So we can express the bending component of the strain as position. So distance from the central axis, which is called the neutral axis, as you may remember from the strength of material course, where the bending of beams was discussed, divided by R. So stress is, of course, E times epsilon 0, so the linear one, plus EY over R, so E times epsilon B. So this is the strain component. Let's say split into two pieces, linear and bending one, and the part that results, the stress that results from temperature change. We have here three such factors. If we make a force balance between the end of the beam, where the force is applied, and any cross section, so the force can be applied at the end. This is the most general case. The force may be zero, so if there is nothing applied, but in general there may be a force. So we have force at the end, and at any cross section we have sigma times A. Okay, so this is E times A epsilon 0 plus 0 here, because we provide the balance, the force balance, at the central line, so at the center of cross section, and at this location y equals 0. So this factor is 0. And minus alpha E. And if there is a distribution of temperature, we have to integrate it over the cross-sectional area. If we have constant material parameters, alpha E, it is of course here. If the material properties are temperature dependent, they would have to be inside the integral. This factor, again, similar as it was in the previous case, we can mark it or name it as a thermal force. which is generated here, and we have here the as before, we have here the temperature distribution across the section. Of course, previously it was symmetrical. Now there is any distribution of temperature across the section. So now we can solve for the epsilon. So the strain at the centroid axis, and this is of course the force applied, the mechanical force applied to the system, plus the thermal force divided by E times A. This is one thing which occurs. The other thing in bending is, or the distribution of stresses, which is we have to fulfill another equation of equilibrium. In previous case, the moment was 0, so it was due to the symmetrical temperature distribution, the moment cancel out. So let's say forces above the center line and below the center line, they cancel out. They produce the same moment, and the moment was always 0. Now we have several components here at the moment. So if we calculate moment with respect to the central line, so the neutral axis, we have sigma y. So sigma dA was a force. Now we have sigma dA as a total force times distance y from the neutral axis. And of course, this moment has to be 0. And here we have the components from the same story from here. Here we have 0 because the force acts in the center, so the moment arm is 0 from the external loading. We have E over R, and here we have E times Y, and now times Y, so we have Y squared over dA. And this factor, as you may recall from, again, the course of mechanics and strength of material, is the moment of inertia. So the integral of Y squared dA. And here we have minus alpha E integral of temperature distribution times Y. And this factor here, the last one, can be again named as thermal moment. So moment which occurs in the material due to the temperature distribution. So the moment that bends the beam. So MT is alpha E integral of delta T Y dA. If this is the case already written, if the materials data are independent on temperature, if they depend on temperature, unfortunately they have to be integrated. And if you recall, again, information from your strength of material course, you had that the beam after bending, so it is a curve. It forms a curve. It is initially straight, but it bends to form a curve. The curvature of this beam, or 1 over radius of curvature, was moment divided by E times I, flexural rigidity. Now we have two moments. One is the mechanical one, and the other is the thermal one. And you may remember that it is the second derivative of deflection, so the vertical movement, over dx. And this is the deflection curve of the beam. So the shape of the beam after deflection. Of course, this is the differential equation. Now we have to first resolve it, solve it, find the y, but y you will get as a function of x. And of course, it will depend on the total moment generated, so the mechanical one and the thermal one. And of course, there is a, let's say, a resistive part which prevents the or constrains the deformation. So the deflection is the power is the product of material property E times the cross-sectional the moment of inertia, which prevents the movements, the rotational movements of particular parts of the beam. If we look at stress in a beam, which can be the result of mechanical and thermal loading, we have here three factors which were discussed before. So the force factor, which results, so this is the, let's say, longitudinal loading, so force which tends to extend or compress the beam, so the normal force. This is the external force, and this is the force due to the temperature distribution. This is the part resulting from moment, so from the effects, rotational effects, and this is m, total m, so mechanical moment and thermal moment divided by moment of inertia, so geometry data, times y, and minus alpha E delta t. So you see that, of course, the stress, as it was always, depend on the location where we calculate the stress. In general, now, in a case where we do not have temperature distribution, so there is no thermal loading applied, the maximum stress occurs always at the outermost fibers if you measure from the central line, so from the neutral axis. In the neutral axis, which is usually which passes through the centroid of the cross section, stress is generally zero. Looking at the mechanical stress only, and the maximum stress is at the outermost fiber, so at the highest distance from the neutral axis. Here it is not necessarily the true, depending on the direction of mechanical moment and direction of the thermal moment. So depending on the temperature distribution within the material. So it may be different depending on the stress distribution. They can add together or they can subtract, so depending on the actual conditions. If T would be a function of both lateral directions, so let's say height and the width of the beam, or the beam would be unsymmetric, the stress would be slightly more complex, determined, so it requires two-dimensional analysis, and the stress can be expressed in a similar form, but here we have the mechanical part. This is the same story as before, but here we have two moments which can be generated. The moments are hidden in the factors ky and kz. They are given here. So we can see what is the amount of moment in z direction, what is the moment. So we have unsymmetric bending actually. So slightly the beam is slightly bent into z direction, slightly bent into y direction. So we have to combine them together. as you may also remember from your structural material course, if you recall that asymmetric bending. So this is the span-wise thermal moment. So in the other direction. So this one is previously was in the vertical direction, and this is in the span-wise direction. So in Z direction. So the definition is very much the same. Here we have only Z coordinate, and of course the distribution depends on what is the temperature distribution in Z direction, and here what is the distribution in Y direction. So there's a combination of these two things. And I'm wondering, okay, because we will now enter a different kind of stresses which require some extra discussion. I think due to the last too long lecture today, we can save the time, so we can finish our meeting today, and we will continue it. So the thermal bending will be continued next time for different cases of beams, and we'll also introduce the case where we have a pipe system. So there's a pipe which has a different distribution of temperature due to different boundary conditions, different thermal conditions due to, let's say, two-phase flow. Let's say we have steam and water, or generally liquid and gas, and we'll see how, due to different thermal conditions, the pipe system can be bent. So it will be connected. So far we discussed it on the beams, and probably you may not be very convinced why we are discussing the beams, but this is the story which happens everywhere. Any foundation, any support, any piping system can be treated as a beam. Everywhere where bending occurs, this is a beam. So you have to only see it where it is, but the formulas are very much the same. So that's why we are discussing the beams, bending of beams, and we'll see how the beam deforms. Next time I'll try to even present it by some numerical examples, and we'll observe some extra effects that occur in this situations when we have different boundary conditions. Okay, if you have any question, you can ask. If not, we will meet. When? After the holidays. Our next meeting is, yes, because next time we'll not have. So the 8th of April will be our next meeting. So you have some free time. Of course, we are all almost closed at home, so you can rest, you can sleep a lot. So have a good time, relax, and we will meet in 2 weeks' time. You'll be fully rested and eager to continue this. This lecture. Okay, do you have any questions? Anyone? If you want to tell something, please unmute yourself.